For years, Vesta, one of the largest objects in the asteroid belt between Mars and Jupiter, was considered just another cold, inert body orbiting the Sun. Then in 2011, the Dawn mission revealed an unexpected truth. Beneath Vesta's seemingly lifeless exterior, there were signs of salty water activity. Imagine a world without an atmosphere in the vacuum of space where any traces of water would vanish in an instant. And yet, as Dawn mapped the asteroid's surface, it captured features that defied expectations. Curving gullies within craters and fan-shaped deposits formed by a past flow of liquid. Scientists were stunned. Vesta had long been regarded as dry and barren, but these findings suggested something revolutionary. The evidence pointed to a past where impacts melted hidden deposits of ice, creating temporary flows of water and minerals that carved paths across the asteroid's surface. According to their theory, salty water might even be hidden within the rock, concealed beneath a desolate surface. This discovery hinted at a far-reaching truth. Salty water may not be an earthbound phenomenon. Across the solar system, from the icy crust of Europa, the salty deposits of Ceres, signs of salt water appear in the most unexpected places. But why does this matter? On Earth, salt water was a key ingredient in the origins of life. Early oceans rich in salts and minerals provided the foundation for the first complex molecules, setting off processes that eventually led to life. Now that salt water is being detected beyond Earth, it raises profound questions. Could it be a common feature of worlds capable of sustaining biology? And if so, could this alter the course of our search for life? Once Earth was a hostile place, shaped by a cataclysmic force that delivered all the ingredients necessary for life to its surface. When the planet's surface cooled, steam and gases condensed, forming the first oceans. But these were not the oceans we know today. These were acidic, mineral-rich from volcanic activity and saturated with salts from the Earth's crust. In these early saltwater pools, the mineral composition began to evolve, creating a unique balance that became fundamental for life. Unlike freshwater, saltwater contained many ions, sodium, potassium, chloride, that promoted essential chemical reactions. The water itself acted as a medium for these ions, allowing them to interact in ways that would eventually lead to self-replicating molecules. Around these vents, where hot water met the depths of cold water, may have been the place where life began. The temperature gradient and the myriad of minerals created a unique chemical environment. The presence of salts and minerals triggered reactions that resulted in molecules that became, in essence, the building blocks of life. Organic molecules, carbon chains, and complex structures began to form, capable of interacting, growing, and ultimately replicating. The hydrothermal vents provided a stable yet dynamic environment. These pockets of salt water functioned as natural laboratories, with salinity playing a crucial role. Salt ions stabilized and protected early organic molecules from breaking down, allowing them to persist and merge into complex forms. These ions also help transfer energy, an essential process for the emergence of metabolic activity. As these molecules became more complex, the presence of salt continued to shape their structure and function. Early cell-like structures, often called protocells, spontaneously formed from fatty molecules, trapping salt water inside. This protocellular environment allowed molecules to stay close together, promoting further interactions. The salt ions, already playing a key role in stabilizing molecules, served another purpose by allowing these cell walls to regulate the intake and output of substances, which turned out to be a primitive form of cellular control. In these primordial oceans, salt water was not just a solvent, it was an active component in the emergence of life. It provided the stability and resources necessary for the first forms of life to survive, and for this reason, scientists today look at these saline conditions as clues, recognizing saltwater as a natural incubator for the earliest building blocks of life. As we look for evidence of saltwater on distant planets and moons, we may catch glimpses of this ancient history. Moreover, beyond its role as the cradle of life, saltwater does not simply sit passively in the ocean. It is a central player in Earth's climate system, moving vast amounts of heat from the equator to cooler regions. The Gulf Stream, one of the most vital ocean currents on our planet, transports warm waters from the Gulf of Mexico along the eastern coast of North America, bending toward Europe. Thanks to this constant flow of heat, Western Europe's climate is much milder than other regions at similar latitudes. But what drives this powerful ocean current? Surprisingly, it's the salinity of the water itself. When warm water flows north, it cools and becomes more dense. This process is intensified near the Arctic, where the formation of sea ice leaves salt behind, making the surrounding water even denser. Heavier salt-laden water sinks to the bottom of the ocean, pushing warmer surface water northward. And this cycle is known as a thermohaline circulation, a conveyor of heat that stabilizes global temperatures. Without this system, the climate balance we know today would change drastically. In temperate regions, such as much of Europe, winters could be much colder, while subtropical areas might face scorching heat and intensified drought. The Gulf Stream is just one current in a global network of saltwater that regulate the climates across continents. However, as climate change accelerates, the system may be under threat. The melting of polar ice caps as a direct result of rising global temperatures is adding large volumes of fresh water to the ocean. This influx of fresh water dilutes the salt level, making the water less dense and slowing down the sinking process. When water stops sinking, circulation weakens, along with the heat exchange that regulates Earth's climate. Scientists have already observed signs of it slowing down. The speed of the Gulf Stream has noticeably decreased. This change has profound consequences not only for the local climate, but also for weather patterns worldwide. As currents weaken, some regions may experience more extreme storms, while others may suffer from drought. This impact even extends to marine ecosystems, as currents transport essential nutrients needed for oceanic life across thousands of miles. Climate models predict that if this slowdown continues, Europe could face much colder winters than today, with potential temperature swings that could disrupt agriculture, energy demands, and even population habits. At the same time, in regions already prone to heat, extreme conditions may become even more severe as the moderating influence of the Gulf Stream weakens. While the Gulf Stream slowing down is one of the most well-documented, it is part of a larger pattern affecting many of Earth's saltwater currents. For example, currents in the Indian and Pacific Oceans play a similar role in regulating climate conditions in Asia and Oceania. Without saltwater currents, Earth's climate would be as variable as the weather. However, the mere presence of salt in ocean water is not a cornerstone of stability that ensures a prosperous future for Earth. Some scientists speculate that just as Earth has undergone cycles of warming and cooling over millions of years, climate change may partially counterbalance the slowing of these currents. However, let's return to the question of salt water as a foundation for essential life functions. As we've already established that, unlike freshwater, salt water contains dissolved ions of sodium, potassium, calcium, and chloride. These ions are essential for biochemical processes that sustain our body's functioning. They move across cell membranes, create electrical currents, and are fundamental to everything from muscle contractions to thought processes. The body relies on salt water's ability to conduct electrical signals to coordinate actions within cells and between them. For example, our nerve and muscle cells send electrical impulses by moving sodium and potassium ions across cell membranes. This movement of ions generates an electric charge that enables nerve impulses to transmit signals from the brain to other parts of the body, enabling complex functions like speech, movement, and even memory formation. The role of salt water is not limited to communication. Inside the cells, ions maintain a careful balance that supports cellular activity. An imbalance of sodium or potassium levels can disrupt these functions, leading to serious health issues. A sodium level that is too low, known as hyponatremia, can cause confusion, muscle cramps, and in extreme cases, seizures. On the other hand, too much potassium or hypokalemia can lead to life-threatening heart arrhythmias. Hydration is another crucial area where salt water plays a vital role. Water alone cannot effectively maintain hydration in our cells. It is the electrolyte balance in salt water that allows our body to retain fluid in the right compartments. When we sweat or lose fluid, we lose these electrolytes, which affects our hydration, blood pressure, and overall cellular function. To replenish them, sports drinks often contain salt, not just to replace lost water, but to restore the ions necessary for proper cellular function. Whether it's maintaining hydration, enabling nerve function, or stabilizing cellular processes, saltwater ions are key elements that sustain our lives. As the world increasingly transitions to renewable energy sources, the demand for efficient, safe, and scalable ways to store this energy is also growing. The dominance of lithium-ion batteries in energy storage solutions today is largely due to their high energy density and long lifespan. However, there are environmental costs of lithium mining and the risk associated with chemical instability. But a promising alternative has emerged on the horizon based on a resource as abundant as the ocean itself, salt. Sodium chloride-based batteries are a renewable, scalable, and economically efficient solution for energy storage. Unlike lithium-ion batteries, saltwater batteries use abundant materials like sodium and iron, elements that are not subject to the same cost fluctuations or scarcity as lithium. The basic design of a saltwater battery is a type of redox flow battery, a system built for long-term energy storage. Inside the battery, salt water acts as an electrolyte, moving ions between two reservoirs, one with positively charged ions and the other with negatively charged ones. The flow generates electricity by moving these ions, allowing the battery to store and release energy as needed. One of the most significant advantages of saltwater batteries is stability. Unlike lithium-ion batteries, which are prone to overheating and in some cases combustion, these batteries operate at lower chemical reactivity. Their non-toxic nature also means fewer safety concerns during thermal runaway, making them an attractive option for large-scale applications. Companies like Infinity Turbine are pioneering the development of saltwater-based batteries, with prototypes promising not only enhanced safety, but also longer-term use. By using inexpensive and widely available material like sodium and iron, saltwater batteries can be manufactured and deployed at a fraction of the cost of lithium-ion. Moreover, these batteries offer unparalleled scalability. In typical redox flow batteries, increasing capacity can be as simple as expanding the electrolyte reservoirs. For grid storage, this flexibility allows for larger batteries capable of storing renewable energy generated by solar and wind power plants over a long period of time. Imagine a future where entire cities are powered by the sun during the day, while salt water holds surplus energy for use at night. However, the potential of human civilization doesn't stop there. By studying the role of saltwater in carbon capture and its potential to combat climate change, recent advancements suggest that saltwater-based technologies could offer a scalable solution. One promising method is using saltwater as a medium in direct air capture systems, where its natural properties help extract and efficiently store carbon dioxide from the atmosphere. Saltwater aids DAC processes thanks to its abundance of ions, which can create a conductive medium ideal for capturing and transporting CO2. For instance, carbon engineering's approach uses an aqueous solution with a high concentration of ions like potassium and calcium to capture atmospheric CO2. Through a series of chemical reactions, CO2 from the air reacts with these ions in the solution, forming carbonate compounds, which are then processed to produce pure CO2 for sequestration or further use. The use of saltwater in DAC not only aids in CO2 extraction but also minimizes energy costs. Water itself acts as a coolant, which is critical given the heat generated in the capture process. Moreover, DAC methods require fewer specialized materials, borrowing from established cooling tower technology, which reduces cost and enables the system to operate continuously by utilizing saltwater's high surface area and constant ion transport capacity. Such systems already demonstrate impressive cost reductions for carbon capture, estimated between $94 and $232 per metric ton of CO2. This significant reduction compared to traditional estimates, which sometimes exceed $500 per metric ton, speaks to the scalability and accessibility of a model that could see widespread use. The environmental impact extends beyond carbon capture. Carbon engineering's model also considers using captured CO2 to produce synthetic fuel, which has direct applications for decarbonizing the transportation and energy sectors. As technology and infrastructure advance, these systems could contribute significantly to climate mitigation efforts, ensuring sustainable progress toward global emission goals. A potential key to extraterrestrial life, saltwater can be found in various environments throughout the solar system. Numerous space missions, including NASA's studies on Europa and Enceladus, focus on the presence of salty oceans beneath their icy surfaces. Europa, one of Jupiter's moons, is of particular interest as its surface shows signs of a subsurface ocean rich in salts and minerals. Scientists believe that these conditions, driven by the gravitational forces of Jupiter, could mimic Earth-like environments where microbial life thrives, such as deep-sea hydrothermal vents. Saturn's icy moon Enceladus also shows potential for life, as observed by the Cassini mission. When Cassini detected salt-rich plumes erupting from fractures in Enceladus's ice shell, it provided direct evidence of a subsurface ocean with a high salt concentration. These plumes, rich in water and organic compounds, indicate a habitable environment below the surface powered by internal heating similar to Europa's. In addition to satellites, signs of salt water have even been discovered on asteroids. NASA's Dawn mission focused on Vesta, a large asteroid in the asteroid belt, and found unexpected traces. Craters on Vesta's surface suggest water activity, likely from meteor impacts that melted subsurface ice and created temporary flows of salty liquid. This discovery supports the idea that even dry, airless bodies can contain salts that stabilize liquid water, which could become a refuge for microbial life in isolated environments. The implications of finding salt water throughout the solar system extend beyond geology. These extraterrestrial oceans, rich in minerals and possibly supporting complex chemical processes, mirror Earth-like environments where life first originated. As we prepare to explore these worlds, scientists hope to find direct signs of life or the building blocks necessary for its development. Meanwhile, we eagerly await future data from NASA's Europa Clipper mission, launched this October, and ESA's JUICE mission, which started last year to study Jupiter's moons. Imagine being able to harness the power of the sun, which has been the lifeblood of our planet for billions of years. Its energy, produced in a process known as fusion, illuminates our world and sustains life. But what if we could replicate this process right here on Earth? What if we could create our own miniature suns to power our homes, our cities, and our world? Sounds like science fiction, doesn't it? But what if we told you that this is not a distant dream, but a reality that scientists have been approaching for decades? In the heart of California, at the Lawrence Livermore National Laboratory, a group of dedicated scientists worked tirelessly on this mission. Their goal? To accomplish nuclear fusion, a feat that could revolutionize the way energy is produced and pave the way for a future of clean, limitless power. And quite recently, at the end of last year, there was a breakthrough that could have changed everything, illuminating our future. Imagine our star, the Sun, 93 million miles away in the vast expanse of space. It is a giant glowing ball of gas that's incredibly hot. Have you ever wondered what makes the sun shine so bright? The answer is both simple and complex: nuclear fusion. In simple terms, nuclear fusion is the process by which two light atoms combine to form a heavier atom. It's like taking two small Lego blocks and putting them together to make a bigger one. But there's a catch. When these atoms combine, they release a huge amount of energy. And they release so much energy that it allows this energy to power the sun and make it shine. Now you may be thinking, that sounds great, but what does that have to do with us here on Earth? Well, if we could replicate this process, we could potentially create a virtually limitless source of clean energy. Imagine your house, your city, and even your car being powered by the same process as the sun. That is what fusion promises us. But this idea is not new at all. Scientists have been dreaming of harnessing the power of fusion for decades. In fact, the concept of nuclear fusion was first introduced in the early 20th century by physicists like Albert Einstein and Hans Bethe. Over the years, there have been many attempts to achieve fusion, from Project Sherwood in the 1950s to the first tokamaks in the 1960s, and the construction of modern facilities such as ITER and the National Ignition Facility in the U.S. Each of these efforts brought us closer to the goal of achieving fusion. Although there have been problems and setbacks along the way, the dream of harnessing star power has never faded. And now, with the recent breakthrough at Lawrence Livermore National Laboratory, we may be closer than ever to making that dream a reality. Just imagine a world in which the light in every house, street, and city is powered not by coal or gas, but by the same process as the stars. As we discussed earlier, fusion is a process in which two light atoms combine to form a heavier atom, releasing huge amounts of energy. But what makes the process so special? Why are scientists around the world so interested in it? Today, most of our electricity comes from burning fossil fuels like coal and gas. These processes release harmful greenhouse gases into the atmosphere, contributing to climate change. Such resources are also finite, which means they will run out sooner or later. But fusion offers another way. Fusion is fueled by hydrogen isotopes such as deuterium and tritium. Deuterium can be extracted from seawater and tritium from lithium, which is abundant in the Earth's crust. This means that the fuel for fusion is almost limitless. And remember, the energy released by fusion is enormous. Just 1 gram of fusion fuel can produce the same amount of energy as 8,000 gallons of gasoline. That's like driving around the Earth more than 300 times. Fusion could generate huge amounts of energy without the carbon emissions associated with fossil fuels. This could help us fight climate change, and move towards a more sustainable future. The outlook for fusion energy extends beyond the scientific community. Political figures such as U.S. Senate Majority Leader Charles Schumer also recognizes its potential. He stated, "This breakthrough is a giant leap toward making fusion power a reality. It marks the beginning of a new era in energy production that is cleaner and virtually limitless. The potential for our economy and the environment is enormous." With the stakes so high, it's not surprising that the fusion race is often compared to the space race of the 20th century. But achieving nuclear fusion is not easy. It requires incredibly high temperatures and pressures, such as those found in the heart of the sun. Also on top of this, for many years, the energy required to start a fusion reaction exceeded the energy it produced. But this is where the Lawrence Livermore National Laboratory and the National Ignition Facility come into play. They're working to make fusion a reality, and their recent breakthrough could be a game changer. Imagine a place where the world's brightest minds come together to solve some of the biggest problems facing humanity. That place is the Lawrence Livermore National Laboratory, or LLNL for short. Located in California, LLNL is a center for scientific and technological innovation. It is home to thousands of scientists, engineers, and other professionals who work on a wide range of projects from national security to environmental science to, you guessed it, fusion. One of the gems of LLNL is the National Ignition Facility, or NIF. This is where the magic of fusion happens. NIF is the largest and most powerful laser facility ever built. It is the size of 3 soccer fields and contains 192 laser beams that can transmit more than 2 million joules of energy. 2 million joules is about the kinetic energy of a car driving down an expressway. So imagine the energy of a car rushing down a highway concentrated at a tiny point in a split second. That's the kind of energy we're talking about when the National Ignition System lasers go off. But what exactly does the NIF do? Its main task is to create extreme states of matter like those found in the cores of stars or inside nuclear weapons. It does this by focusing its 192 laser beams on a tiny target, creating temperatures and pressures that are several times higher than those at the center of the sun. The target is a tiny capsule filled with fusion fuel, which is a mixture of hydrogen isotopes deuterium and tritium. When the lasers strike the target, they detonate the fuel, triggering a fusion reaction. But the road to this point was far from easy. As LLNL Director Dr. Kim Boodle says, "The quest to ignite fusion in the laboratory is one of the most significant scientific challenges ever undertaken by humankind, and its achievement is a triumph of science, technology, and above all, people. Overcoming this threshold is a vision that's led to 60 years of focused inquiry, a continuous process of learning, building up, expanding knowledge and capabilities, and then finding ways to overcome new problems that arise. These are the problems for which U.S. national laboratories were created." NIF is a marvel of modern technology and science, and it's played an important role in advancing our understanding of nuclear fusion, but it's not just about science. The work being done at NIF may one day lead to a world powered by clean, abundant fusion energy. So how did scientists achieve these results? Let's delve into the details of the achievement and how it brings us one step closer to such a future. In December 2022, something extraordinary happened at the National Ignition Center. For the first time, a man-made device achieved a fusion reaction that produced more energy than was consumed. This is known as fusion ignition, and it's really important. But what exactly does fusion ignition mean? So remember how we talked about fusion like connecting 2 small Lego blocks to make one bigger? Fusion ignition is similar to that, but with a twist. Instead of just joining two blocks together, you join so many blocks that the energy release starts a chain reaction, causing more and more blocks to join together on their own. It's like lining up a row of dominoes and knocking over the first one. That first knuckle knocks over the second, which knocks over the third, and so on until all the knuckles fall. Well, that's exactly what happened in the NIF experiment. The energy from the lasers triggered a thermonuclear reaction that continued on its own, releasing more energy than it took to trigger it. But achieving this has not been easy. As Dr. Arati Prabhakar, Chief Science and Technology Advisor to the President, says, "We have had a theoretical understanding of fusion for more than a century, but the road from knowledge to action can be long and difficult. Today's milestone shows what we can do with persistence." Once again, as the sun sets, we're left to wonder, what if we could harness the power of the stars to light our cities, power our homes, and grow our industries? But what would a world powered by fusion energy look like? First, fusion energy is clean. Unlike fossil fuels, it produces no greenhouse gases or harmful pollutants. This means it could play a crucial role in combating climate change and improving air quality. In addition, fusion energy is safe. There's no risk of meltdown as in a nuclear fission reactor, and it produces no long-lived radioactive waste. In the event of a malfunction, the reaction simply stops. We have an enormous supply of fusion energy. The fuel for fusion is water and lithium, which is in abundance on Earth. This means that the fusion energy can provide a virtually unlimited supply of energy, reducing our dependence on limited resources like oil and gas. But while the potential benefits of fusion energy are enormous, there's still many problems to be solved. Fusion reactions require extreme conditions that are difficult to achieve and maintain, and the technology to capture and convert fusion reaction energy into usable electricity is still in the early stages of development. However, the event itself gives us grounds for optimism. It shows that fusion ignition is possible and that we are on the right track. Thanks to continuous research and development, the dream of a world powered by fusion energy can become reality. But what does the future hold for fusion energy? Although the recent achievement of fusion ignition is a milestone, it's only the beginning. There's still a long way to go before fusion energy can be used on large scales to power our homes, cities, and industries. Future research will focus on several key areas. First, maintaining the extreme conditions required for fusion reactions is a major challenge. Second, we need to develop the technology to capture and convert the energy produced by these reactions into useful electricity. This will require overcoming numerous technical challenges, from handling the intense heat and radiation produced by the reactions to finding materials that can withstand these conditions for long periods of time. Another important step is to scale up these reactions to a size that could power a city. Designing and building a fusion power plant that could operate continuously and reliably is an important challenge. This applies not only to the fusion reactor itself, but also to the infrastructure for fuel supply, energy capture and conversion, and waste management. However, the potential benefits are enormous. Fusion energy could revolutionize our energy system, providing a virtually unlimited supply of clean and safe energy. It could help us fight climate change, improve air quality, and reduce our dependence on limited resources such as oil and gas. The road to fusion energy is a marathon, not a sprint. It will require continued investment in research and development, cooperation among scientists around the world, and the support of politicians and the public. But still, a promising start has been made. The recent breakthrough at the National Ignition Facility is a beacon of hope, lighting the way toward a future based on clean, abundant energy. And the farther we look into the future, the brighter the prospects for fusion energy shine. One thing is certain: the day will come when star power will no longer be a distant dream, but a reality within our reach. At some point of our lives, we have probably all wondered if we are alone in the universe. It would seem that in our own or in other distant galaxies, there are so many planets that revolve around numerous stars. So why have we still not encountered any traces of extraterrestrial life? But what if advanced alien life forms have been around for a long time, and they're simply hiding? According to the dark forest hypothesis, technologically advanced civilizations outside of the solar system may already be thriving. However, they have no intention of making contact because they are either cautious of potential attacks from other civilizations, or they may be indeed preparing to attack. Today, you'll learn about the dark forest theory and why you should probably be afraid of being heard by someone in the vast cosmos. 1. The dark forest hypothesis, the author and original source. The author of the Dark Forest Hypothesis, DFH, is science fiction writer Liu Cixin. It's worth noting that this is not a scientific theory, and it's not based on any concrete evidence. In 2008, Liu Cixin published his successful fiction novel titled The Dark Forest. The Dark Forest theory was first outlined in this book. The gist of the theory is that every civilization on a cosmic scale seeks to obtain the resources necessary for its continued survival. Therefore, any extraterrestrial life hides in order to not be destroyed by another civilization, and also in order to be able to attack and ensure its own survival. So why is this theory called the Dark Forest Hypothesis? In his novel, Liu Cixin compares this to precarious coexistence to a forest inhabited only by hunters. The author paints civilizations as metaphorical armed shooters in a dark forest, who silently move forward, afraid of being discovered by fellow hunters. If one hunter managed to find another, it's in their best interest to attack first before the enemy does the same. Based on this, we can name several ideas that are promoted by DFH. First one is that hypothetically, alien civilizations exist, but they are in hiding due to the risk of being attacked by others and losing acquired resources, such as inhabited planets. Within the construct of the Dark Forest Hypothesis, survival as the basis of every civilization is known as the chain of suspicion. This phenomenon is caused by insufficient communication, which leads to mistrust as a direct result. The second idea is that a civilization that gives away its location by actively transmitting, say, radio signals, could be captured or destroyed by others for resources. The third concept is that fellowship in this type of system is exceedingly rare, since every civilization strives above all to survive through expansion. However, a treaty is possible if the terms are beneficial to both civilizations. Liu Cixin represents the universe as a battlefield for limited resources, where an alliance is practically impossible. Finally, it's important to note that in Liu Cixin's hypothesis, these hunters are analogous to civilizations with a high level of technological advancement. Therefore, if any civilization is not sufficiently developed to announce itself in space, it will either go unnoticed or it may become easy prey. 2. DFH is an answer to the Fermi paradox. As you may already know, in 1950, famous physicist Enrico Fermi, when discussing the phenomenon of flying saucers with his colleagues, unexpectedly asked, "Where is everyone?" referring to examples of extraterrestrial life which marked the beginning of the famous Fermi paradox. We discussed it in detail in this video on our channel. Fermi assumed that if our galaxy formed several million years before the birth of mankind, then it is possible that other civilizations could have emerged during this period, much older than Earthlings. Therefore, the Milky Way galaxy should be full of civilizations, which could pick up our signals due to their much more advanced technological development, as well as travel through the galaxy. However, so far we have not seen any traces of alien activity. Why haven't they visited Earth yet or come close to our planet? To determine the potential number of extraterrestrial civilizations that exist within our galaxy, the famous Drake equation was derived in 1961. However, we cannot use it to learn why alien creatures have not left any signs of their life. Therefore, at the moment, the Fermi paradox only has theoretical explanations. Additionally, according to physics professor Adam Frank, the probability that Earthlings are the only civilization in the universe is very small. 1 in 10 billion trillion, which is to say 1 times 10 to the 22nd. The professor suggests that our evolution was not unique and other civilizations could potentially have existed before us or even much longer before us. There are more than 70 hypothetical solutions to this issue, one of which is the dark forest hypothesis. Of course, we cannot check the veracity of DFH due to our current technological limitations. However, Liu Cixin's theory provides a logical explanation as to why we still haven't picked up a single alien signal or found any clear signs of life on other planets. It's simply dangerous for other civilizations to betray their location for fear of invasion. Although this hypothesis presents very clearly defined ideas, DFH still has some inaccuracies. For example, if other civilizations exist, then they must differ from ours when it comes to the level of development due to different periods of origin, as Fermi pointed out. This means that there may be civilizations of our technological level or higher that actively search for alien life or study their own systems just like us, because they don't see it as a threat. Therefore, we may not be the only ones sending signals out there, because civilizations do not necessarily develop in fear of detection if they have not experienced confrontation. 3. More about the assumptions of dark forest hypothesis. The idea of capturing other territories and the possible destruction of the first civilization on a cosmic scale is reminiscent of our historical experience on Earth, namely colonization and wars. There are a lot of reasons why people conquer and establish power over other nations. However, in most cases, such as during the colonization of Africa by the Europeans in the 19th century, the main motivation were land and natural resources. The rapid industrial development in Europe required more resources, which were abundant on another continent. Therefore, the colonization of Africa contributed to the development of European countries. But the African land and its population suffered from this expansion. The DFH offers the same colonial model as the reason why one civilization would attack another. We're still pursuing the goal of expansion for the continued survival of mankind, studying exoplanets and other star systems, and planning the colonization of Mars. The red planet is also rich in natural resources that are needed for technological development. Therefore, if we assume that another civilization pursues the same goals, we may have to fight for lands that could serve humanity. Otherwise, our survival would be under threat because, according to this hypothesis, survival and the necessary resources are crucial for the preservation of the species. In addition to the need to replenish a limited resource, there are other reasons for the aggressive behavior by civilizations. For example, as we've already said, the DFH introduces a concept known as the chain of suspicion. This concept is closely related to another aspect of this hypothesis, which is known as the technological explosion. The gist of the chain of suspicion is that it's impossible for civilizations to know whether others are benevolent or hostile. These doubts can lead to preemptive attacks and self-defense. According to the researcher Chao Yu, this chain can only emerge between civilizations with the same level of technological development, since they can likely objectively assess their own and other people's capabilities. Thus, if there is a significant gap in their respective levels of development, the chain cannot be formed. The technological explosion describes the ability of cosmic civilizations to make rapid scientific and technological leaps. A strong new hunter can pose a threat to others, because advanced civilizations can start to be wary of it or seek to destroy it. However, Chao Yu points out that any invasion attempt could also harm the attacker, as other civilizations with similar or higher levels of advancement would be able to detect it, which would contribute to the chain of suspicion. However, in spite of the clear advantage in attacking other civilizations and in stealth, the DFH considers another scenario: benevolence. The point of benevolence is to refuse to attack other civilizations, even if they are detected, and they will probably be able to respond to the signal. In a dark forest, this tactic is very dangerous because it is again reinforced by the chain of suspicion. Found by a benevolent civilization, another civilization may turn out to be aggressive or rapidly developing. Therefore, in the future, it will be able to destroy others and survive, having collected enough resources, whereas the benevolent civilization will most likely cease to exist. If we assume that extraterrestrial life really exists, and it is way more advanced than us, then it might attack us, since this is a survival tactic with the highest chance of success. This is not the best news. So then, are there other ways for the events to unfold that are beneficial for Earth based on the dark forest hypothesis besides an attack on our planet? Let's look at this in terms of game theory. Number 4, game theory and DFH. The point of game theory is to learn how people make decisions based on certain conditions in order to achieve the best result. So let's imagine Earth as civilization A and a more advanced alien life as civilization B. Let's assume that B has picked up on our radio signal. Now B has 3 strategies for action: attack, remain unnoticed but become suspicious, or respond with a prospect of possible friendship. Attack will be considered the most advantageous strategy, even if A is able to fight back. On the other hand, this scenario might turn out to be a losing one for B if A, according to researcher Alina Su, can send a signal in order to transmit the coordinates of the planet of civilization B to other civilizations. Perhaps in this case, the best option would be to remain unnoticed. If both civilizations don't do anything, neither will benefit. On the one hand, this will save A and B from danger, but on the other hand, they won't be able to obtain the necessary resources. There's also an option to make friends. If both civilizations agree to an alliance, then one of them will benefit, for example, from the ability to use alien technology. The other civilization, the one that proposed friendship, would also be able to benefit, albeit slightly less. Does that mean that an alliance is the best scenario for both civilizations? Possibly, but it comes with some caveats. Firstly, benevolence, as you already know, is very dangerous because, hypothetically, extraterrestrial civilizations are unlikely to be friendly too often. Secondly, the potential amount of resources that would be obtained, even if a trade deal is established, is less than what you would gain with a forced takeover. And so, the theoretical attack on Earth has the highest probability, but this course of events can greatly harm the attacker. Still, other civilizations may be afraid of the unknown military potential of Earth, and therefore choose the tactics of secrecy or friendship. 5. The danger of sending signals into space. Does it mean that if the probability of Earth being conquered is higher than any other option, should we be wary of the propagation of our signal into space? According to DFH, messages to other civilizations could threaten our security, The same opinion is shared by many astrophysicists, including Stephen Hawking. After a breakthrough in space research in the middle of the last century, there was plenty of interest from scientists in the search for alien civilizations. In 1974, the famous Arecibo message was sent to a star cluster 21,000 light-years away. Since that time, several radio messages have been launched into space, the latest of which dates back to 2017. Physicist Stephen Hawking believed that these messages could lead to the scenario described in the dark forest. According to him, an alien civilization visiting Earth could have the same consequences for us as the effects colonization of America had on its native inhabitants in the 15th century. Therefore, he expressed an opinion that this type of communication must be stopped. Nonetheless, other scientists, including SETI astrobiologist Douglas Vakoch, believe that the fear of sending messages can lead to Earth's isolationism. Moreover, Vakoch pointed out that the alien civilizations have had a chance to attack our planet while it was just developing, so you should not be afraid of the possibility of being heard by extraterrestrial life. Finally, the dark forest hypothesis also promotes the idea of differences in hunters' behavior. That is, not all alien civilizations would definitely attack us if they detected our signal. Additionally, a group of independent researchers led by the Global Catastrophic Risk Institute, Seth Baum, suggested that in addition to potentially dangerous civilizations, those with a lesser potential to harm us may also exist. They believe that there might be neutral civilizations that prefer to hide and not make contact, as well as civilizations that could establish a friendly relationship with Earth and help us solve global problems. In conclusion, the dark forest hypothesis is not the sole answer to the burning question, where is everyone? There are many other suggestions that attempt to explain the lack of a hint of extraterrestrial life, such as too great of a distance between civilizations, or the low likelihood of the emergence of other living organisms. Nevertheless, we cannot rule out the possibility of the veracity of Liu Cixin's theory, but we cannot confirm it either. Have we finally found the answer to one of humanity's oldest questions? Are we alone in the universe? The James Webb Space Telescope may have just brought us one step closer to a revolutionary discovery. Meet K2-18b, a distant exoplanet that has suddenly found itself at the forefront of astrobiological research. Why? Because James Webb discovered something unusual in its atmosphere, something that could potentially signal the existence of life. Water vapor, methane, and even the rare dimethyl sulfide are not just random molecules. They may be the biosignatures we are looking for, clues that life in some form exists beyond Earth. Armed with the most advanced space technology ever created, James Webb is our new guardian of the galaxy, a telescope designed to peer into the unknown and perhaps redefine our understanding of life itself. So, are you ready to venture into the unknown and dive into the mysterious world of K2-18b? As we venture deeper into space in search of answers to questions that have puzzled humanity for generations, we rely on the eyes of our technological marvels to bring the universe into focus. One such eye is the James Webb Telescope, or JWST. For decades, the Hubble Space Telescope has been our window to the universe, producing images that have both delighted and enlightened us. But even Hubble has its limitations. Meet James Webb, a telescope dedicated to pushing the boundaries of what we can see and understand. One of the most innovative features of the JWST is its cool screen technology. This is no ordinary sunshade. It's a multi-layered engineering genius the size of a tennis court that blocks the heat of the sun, earth, and moon. Why is this important? Because it allows the telescope to cool to incredibly low temperatures, increasing its sensitivity to the faint infrared signals emitted by distant celestial bodies. Infrared observations are crucial for studying exoplanets such as K2-18b. Unlike visible light, which can be absorbed or scattered by space dust, infrared waves can overcome such obstacles, giving us clearer and more detailed images. JWST's ability to make infrared observations is not just an achievement, it is a revolution in the way we study distant worlds. So what discoveries await us when we turn his gaze to K2-18b? Located 124 light-years away in the constellation Leo, this exoplanet is more than just a distant rock. You may have heard of the Goldilocks zone, a term describing the habitable zone around a star where conditions are ideal, neither too hot nor too cold, for liquid water to exist. K2-18b orbits around its parent star, K2-18, in just this zone. But what sets it apart from other exoplanets in similar orbits? K2-18b is not just another rocky planet. It is what scientists call a Hycean world. Hycean worlds characterized by a hydrogen-rich atmosphere and a surface covered by a watery ocean represent a new frontier in our search for extraterrestrial life. They offer conditions that may be similar to those around hydrothermal vents on Earth, which are known to support diverse ecosystems. Recent observations by the James Webb Space Telescope have revealed intriguing details about the atmosphere of K2-18b. From water vapor to methane and even potential traces of dimethyl sulfide, the atmosphere of this distant world is a cocktail of elements and compounds that could support life, or at least life as we don't yet know it. The discovery of these atmospheric components has caused a wave of excitement in the scientific community. Researchers are full of excitement and speculation as they ponder the implications of these discoveries for astrobiology and the broader quest to understand the nature of life in the universe. Could this Hycean world with its unique atmospheric composition be the key to unlocking the mysteries of extraterrestrial life? And what might its unique conditions mean for the future of astrobiology? When we venture into the field of exoplanet exploration, one of the most challenging but rewarding aspects is the study of alien atmospheres. K2-18b, with its unique location in the habitable zone and intriguing atmospheric composition, provides a compelling example. While Earth's atmosphere is a mixture of nitrogen, oxygen, and gas impurities, K2-18b is a very different cocktail. This exoplanet's hydrogen-dominated atmosphere with traces of water vapor, methane, and perhaps even dimethyl sulfide is a treasure trove of scientific curiosities. Studying the atmosphere of an exoplanet more than 100 light-years away is not an easy task. It involves a technique called spectroscopy, which analyzes the light from the planet's parent star as it passes through the planet's atmosphere. Different molecules absorb light of specific wavelengths, creating a unique fingerprint that can be deciphered to determine the composition of the atmosphere. The infrared capabilities of the James Webb Space Telescope played an important role in these discoveries. The Mid-Infrared Instrument Spectrograph, abbreviated MIRI, allows for an extended range of wavelengths, allowing it to detect a variety of molecules that were previously elusive. The presence of methane and the lack of ammonia in K2-18b's atmosphere has scientists speculating about the types of life that might exist there. On Earth, methane is often produced by biological processes, and its presence on K2-18b opens up the possibility of life forms that thrive in a hydrogen-rich environment, something we've never encountered before. The composition of K2-18b's atmosphere also suggests the presence of a subsurface ocean. This opens up exciting questions about atmosphere-ocean interactions and how these dynamics might affect the overall habitability of the planet. So could its atmosphere be the key to a new understanding of habitability and life beyond Earth? When we think of life, we often imagine Earth-like environments, but in fact, life exists in environments where we can't even imagine. Studying extremophiles, organisms that thrive in extreme environments, opens up new possibilities for studying life beyond Earth. Deep in Earth's oceans, hydrothermal vents spew hot, mineral-rich water, creating an environment devoid of sunlight, but teeming with life. Extremophiles such as the thermophiles and acidophiles thrive there, challenging our traditional understanding of what life needs to survive. Could such life forms exist on exoplanets like K2-18b? The hydrogen-rich atmosphere of K2-18b offers unique conditions for previously unexplored life. On Earth, certain microbes called methanogens produce methane in an oxygen-free environment. If methane in the K2-18b atmosphere is produced biologically, we may be in a world where hydrogen-loving extremophiles thrive. The study of extremophiles expands the range of conditions in which life can exist. From the acidic rivers of Rio Tinto in Spain to the tundra of Siberia, life on Earth exists in a wide variety of extreme environments. This diversity encourages us to reconsider the ecological limits of extraterrestrial life. The potential for a subterranean ocean and hydrogen-rich atmosphere makes K2-18b an attractive target for studying extremophiles in the exoplanet environment. Perhaps this distant world has its version of extreme life, adapted to such conditions and considering them a name for itself. If extremophiles do exist on K2-18b, what might be their evolutionary trajectory? On Earth, life began with simple, single-celled organisms and evolved into complex forms. Could a similar process occur in other worlds given enough time and the right conditions? One of the most interesting aspects of studying the K2-18b atmosphere is the potential presence of dimethyl sulfide or DMS. On Earth, this compound is often produced by marine phytoplankton and serves as a potential biosignature. But could its presence on an exoplanet like K2-18b also indicate life? In the Earth's oceans, DMS is produced by phytoplankton and serves many ecological functions. It is a compound that, when oxidized in the atmosphere, can lead to cloud formation. Its presence in exoplanet atmospheres, such as that of K2-18b, could be a game changer in the search for extraterrestrial life. The potential detection of DMS on K2-18b is still being tested. The James Webb Space Telescope's mid-infrared instrument spectrograph is capable of detecting such complex molecules, but confirming their presence requires careful analysis and expert judgment. The discovery of potential biosignatures such as DMS at K2-18b has excited the scientific community. However, like any groundbreaking discovery, it's also sparked a debate that oscillates between skepticism and optimism. The scientific community is divided on the implications of the discovery of DMS on K2-18b. While some consider it a strong candidate for biosignatures, others warn that abiotic processes can also produce similar compounds. The debate emphasizes the complexities and challenges in interpreting exoplanet data. Historically, astronomical discoveries have often been met with skepticism. When Galileo first discovered the satellites of Jupiter, his findings were initially rejected by many. Similarly, the discovery of the first exoplanet in 1995 was met with caution. These historical examples serve as a reminder that skepticism is an integral part of the scientific process. The search for extraterrestrial life doesn't depend on a single molecule or observation. Scientists are looking for a combination of biosignatures to create compelling evidence for the existence of life. Could DMS be a part of a larger puzzle involving other biosignatures like methane and water vapor? The debate's likely to continue until additional data is collected. As technology advances, future missions with even more sensitive instruments may provide the confirmation needed to classify the DMS as a true biosignature. Is DMS the key we have been waiting for in the search for alien life, or is it a distraction that is throwing us off track? Either way, the debate itself is a testament to the ever-evolving nature of scientific research. The James Webb Space Telescope has revolutionized our understanding of exoplanets like K2-18b, but it's just one step in a long journey of space exploration. What lies beyond this monumental mission, and how will future technologies continue to expand our cosmic horizons? The extremely large telescope, scheduled for completion by 2025, promises to be another game changer. With a main mirror diameter of 128 feet, it will be the largest near-infrared optical telescope in the world. Its unprecedented sensitivity could confirm or refute the biosignatures detected by the James Webb Space Telescope. The Large UV Optical IR Surveyor, or LUVOIR, is another mission on the horizon that could complement James Webb's findings. Designed to operate over a wide range of wavelengths, LUVOIR can provide even more detailed atmospheric analysis and potentially obtain direct images of exoplanets. As we target more distant exoplanets, advances in propulsion technology will be critical. Components like ion propulsion and even theoretical methods involving antimatter propulsion could drastically reduce travel times, allowing probes to reach and study exoplanets within a human lifetime. We've previously published a video on the possibility of interstellar travel and the challenges associated with it. As we stand on the threshold of potentially revolutionary discoveries, it's worth pausing to consider the philosophical implications and questions that fuel our cosmic curiosity. What does the search for extraterrestrial life mean for our understanding of existence, and what questions does it pose for the future? One question that's becoming relevant is the role of red dwarfs in the galaxy. Could these numerous stars, often overlooked because of their small size and dim light, actually be the cradle of life? Their longevity and stability make them intriguing candidates for planets that have life. What will the discovery of extraterrestrial phytoplankton mean for our understanding of life? Such a discovery would not only confirm the existence of life beyond Earth, but would also suggest that the building blocks of life are more universal than we thought. What will the next decade reveal in our quest to understand the cosmos? Will we confirm the existence of extraterrestrial life? Or will we discover new, even more complex questions that challenge our understanding of the universe? The observable universe spans 93 billion light years, a distance beyond our comprehension. In this cosmic space are more than 2 trillion galaxies, each teeming with billions of stars. The scale of the universe is a marvel, but it is not just its size that fascinates us, it is its complexity. The cosmic web, a network of galaxies and dark matter, forms a structure that resembles a vast, interconnected network. Now let's travel to a place equally complex and impressive, the human brain. Composed of some 86 billion neurons, each neuron in the brain is connected to thousands of other neurons, forming a network of unprecedented complexity. The striking similarities between the cosmic web and neural networks are more than a poetic metaphor. It's a scientific curiosity that's led researchers to explore the quantitative similarities between the two systems. Could it be that the universe with its billions of galaxies is reflected in the complex neural networks of our brains? Are we, in some deep sense, a reflection of the cosmos itself? Could it be that the great design of the universe is reflected in the very essence of our being? Do the laws that govern the stars also govern the complex dance of neurons in our minds? These questions, once the domain of philosophers, are now being explored by scientists who are uncovering a connection that may be the key to understanding not only the universe, but also ourselves. Since the dawn of human consciousness, we've been attracted to patterns. The first humans looked up at the night sky, recognizing constellations and tracing the predictable movement of celestial bodies. They observed the cycles of the moon, the changing seasons, and the complex symmetry of leaves and shells. This innate ability to find patterns in nature is not just curiosity. It's a fundamental aspect of our intelligence, the way we understand the world around us. As we evolved, our understanding of patterns changed. We began to realize that these patterns were not simple coincidences, but were governed by fundamental principles and laws. The ancient Greeks discovered the golden ratio, a mathematic constant found in architecture, art, and even the human body. Mathematicians such as Fibonacci discovered sequences that describe the growth patterns of plants and the spiral motion of galaxies. Natural patterns are not limited to static shapes and numbers. They are dynamic, unfolding in time and space. The branching of a tree, the winding course of a river, the swirling of clouds. Everything is subject to mathematical patterns and fractal geometry. These patterns are self-similar. That is, they look the same at any scale, whether you're looking at a single leaf or an entire forest. In the modern age, our search for patterns has led to revolutionary discoveries. The double helical structure of DNA, the strange world of quantum physics, and the butterfly effect and chaos theory all reveal a universe governed by patterns and laws. These discoveries have not only expanded our understanding of the universe, but have also shaped our technology, medicine, and philosophy. But what drives this relentless search for patterns? Is it simply a survival tool, or does it hint at a deeper connection between us and the cosmos? Could our ability to recognize patterns be a reflection of the inner order of the universe, a cosmic signature imprinted in our very being? In a field of scientific research where the mysteries of the cosmos meet the riddles of the human mind, the research of Franco Vazza and Alberto Folletti serve as a beacon of innovation. Their pioneering work has opened new doors in our understanding of the universe and neural networks, revealing striking similarities that challenge our very perception of reality. At the heart of their research is a question that's intrigued scientists and philosophers alike. Is there a connection between the structure of the universe and the neural networks in our brains? Vazza and Folletti have plunged headlong into exploring this question using cutting-edge technology and mathematical models. Their approach was quite quantitative and focused on the distribution of matter in the cosmic web and the connections between brain neurons. By analyzing large data sets and applying advanced algorithms, they found that the structure of the universe and neural networks obey a similar pattern known as degree distribution. A staggered distribution is a mathematical relationship in which a small number of nodes have many links and most have only a few links. This pattern is found in a variety of natural phenomena, from the internet to social networks. Vazza and Folletti found that the same pattern exists in both the cosmic web and the neural networks of the brain. The implications of this discovery are profound. It suggests that the universe and the human brain share a common architecture, a universal structure that transcends scale and complexity. This connection is not just a poetic metaphor, but a scientific reality, a cosmic signature that resonates in the very fabric of existence. The innovative research of Franco Vasa and Alberto Folletti has ignited a spark in the scientific community. Their discovery of structural similarities between the universe and neural networks has opened new doors, leading to a lively dialogue among experts. Dr. Alberto Folletti commented, "Our study is just the beginning of a longer story. We have shown quantitative similarities between these two systems in structural terms. The architectures of these complex networks look strikingly similar. Combining the efforts of neurobiology and astrophysics can expand our ability to get more results." The significance of their findings goes beyond mere academic curiosity. From understanding dark energy to the development of artificial intelligence, the potential applications are enormous. Dr. Alberto Folletti also added, "If we can demonstrate the similarities between a network such as a neural network and the structure of the universe, we may be able to gain more detailed information about the universe and galaxies. This merging of analysis tools from two different disciplines may help in accelerating the process of developing artificial intelligence or artificial neural networks." But the study has also sparked reactions outside the scientific community. Some have used the results to justify creationist theories or New Age viewpoints. Vasa and Folletti clearly emphasized that their work is based on scientific research and has nothing to do with creationist theories or metaphysics. The future of this research is filled with hope and curiosity. Both researchers express a desire to continue exploring this area by looking deeper into the comparison of these two complex systems. They believe that these results need to be analyzed with more sophisticated tools and that the next steps involve moving to a higher level of complexity comparison. As we delve into the mysteries of the mind and the cosmos, we enter a paradox that has both fascinated and puzzled thinkers for generations. In the vast expanse of the universe, where time and space stretch beyond comprehension, lies a paradox that has baffled philosophers and scientists alike: the paradox of Boltzmann's brain. This paradox is named after 19th century physicist Ludwig Boltzmann, and it delves into the very nature of reality and our understanding of consciousness. Boltzmann's original idea was rooted in statistical mechanics, which studied the probability of random fluctuations in a system. Imagine a universe filled with chaos where particles are in constant motion. In this chaos, there's negligible chance that the particles could randomly line up and form a self-conscious brain. This brain, existing for a fleeting moment, would have thoughts, memories, and perceptions of reality, all without a body or a world to live in. The paradox arises when we take into account the vastness of the universe and an infinite amount of time. Given enough time, the random formation of such a brain becomes not just possible, but inevitable. This leads to the unsettling conclusion that it's more likely for a solitary, self-aware brain to exist in the void than for our entire observed universe to have evolved it as it has. The implications of the Boltzmann brain paradox are profound and disturbing. If the existence of such a brain is more likely than the existence of our universe, what does this say about our reality? Are our perceptions and experiences merely illusions? Are we too just momentary fluctuations of cosmic chaos? The paradox has sparked debate and reflection among philosophers, scientists, and thinkers. Some see it as a challenge to our understanding of probability and the nature of existence. Others see it as a metaphorical exploration of solipsism, the philosophical idea that only the mind of man necessarily exists. From Boltzmann's enigmatic brain paradox, we venture further into the uncharted territories of consciousness. The question that has intrigued scientists and philosophers alike is whether the universe itself can be conscious. The idea that the universe may possess consciousness is not new. This concept has been explored in various philosophical traditions and resonated in some scientific theories. Historically, the concept of a conscious universe has been associated with panpsychism, the philosophical view that all things possess consciousness. This idea has been adopted by some Eastern and Western philosophical traditions, suggesting that consciousness is a fundamental aspect of reality. In the realm of science, theories suggesting that the universe may possess consciousness have emerged from the study of quantum mechanics. Some interpretations of quantum theory suggest that consciousness plays a role in the collapse of the wave function, implying that the observer and the observed are interconnected. Cosmologists and neurobiologists have also explored this concept to understand how consciousness might manifest itself on a cosmic scale. Theories such as Integrated Information Theory, or IIT, suggest that systems with a high degree of complexity and integration may possess consciousness. This leads to the tantalizing possibility that the universe, with its complex web of galaxies and cosmic structures, may have a form of consciousness. The idea of a conscious universe is still a subject of debate and research, yet it's firmly planted in the realm of speculation. Although it encourages us to think about our place in the cosmos and the interconnectedness of all things, the idea enters metaphysical territory and should therefore be treated with caution and critical thinking. Having considered speculative ideas of a conscious universe, we turn our attention to a more grounded and scientific theory, the fundamental theory of consciousness of Donald Goffman. Dr. Donald Goffman, a renowned neuroscientist and philosopher, has devoted his life to unraveling the mysteries of consciousness. His groundbreaking theory seeks to explain one of the most mysterious phenomena in existence, the nature of conscious awareness. Goffman's theory is built on the premise that consciousness is not simply a byproduct of complex computations in the brain. Instead, he argues that consciousness is a fundamental aspect of reality akin to space and time. Drawing on quantum mechanics, neurobiology, and philosophy, Goffman's theory explores the interplay between micro and macro levels of existence. He suggests that consciousness arises from the complex interactions of quantum particles within the brain, governed by principles beyond traditional physics. Goffman's work has led to new experiments and collaborations across scientific disciplines. His theory's been tested through rigorous empirical research using advanced technology to explore the depths of consciousness. Although Goffman's theory has received the support and admiration of many in the scientific community, it has not been without controversy. Critics argue that the theory's reliance on quantum mechanics and its bold claims about the nature of reality require further confirmation and study. Nevertheless, Donald Goffman's fundamental theory of consciousness offers a new view of consciousness that bridges science and philosophy. The connections between the universe and neural networks go beyond mere scientific curiosity. They open the door to deep philosophical reflection and have broader implications for our understanding of existence. These connections invite us to see the universe not as a collection of isolated objects, but as an interconnected network of relationships. They inspire new ways of looking at technology, ethics, and our responsibilities as inhabitants of the cosmos. The study of the universe and consciousness has been a central theme of philosophy for millennia. From ancient Greek thinkers to modern philosophers, the quest to understand reality, existence, and our place in the universe has shaped human thinking. Some see the universe as a deterministic machine, while others take a more mystical view. The connections between the universe and the mind only add a new dimension to this age-old debate. The idea of interconnectedness is not just a scientific observation, it is a call to reflection. It invites us to see ourselves as part of a greater whole, realizing the delicate balance of life and the universe. It forces us to think beyond ourselves and consider the impact of our actions on the wider cosmos. The journey ahead promises exciting discoveries. While the connections between the universe and neural networks are fascinating, it's important to approach them with scientific rigor. Misinterpretations and sensationalism can lead to misunderstandings and detract from the true scientific value of these discoveries. So let our curiosity guide us in our explanation of the cosmos, and let our critical thinking help us stay grounded as we continue to explore the uncharted territories of understanding the universe.